Hello. I don't know what time of day we're going to be viewing this, so I don't know whether to say good morning or good afternoon. But we're going to finish up what we were discussing for the whole term. So the last thing we have to talk about is one sample tests of hypothesis. And that will wind up everything to where you'll be prepared for Stats 2 or prepared to just fulfill all the objectives of Stats 1. So let's begin, maybe just like we were in a class, and we'll see how we do. The homework assignment will just be written on the regular weekly assignment, so go in and check that out as well. So this week we're going to talk about hypothesis, and we know that that is just a best guess, right? So when we are trying to decide if something has improved, changed, gotten worse, stayed the same, we're making a hypothesis about this statement, and that's what hypothesis testing is all about. We want to go ahead and look for some critical values. We're still going to be using our Z and our T. We're going to be using our level of significance, but we're adding to it this idea that we are going to try to disprove our null hypothesis, our original hypothesis. And we don't ever quite prove it. We always assume it is true. And so the burden of proof is with our alternate explanation. There are some steps for hypothesis testing. I will let you go ahead and read those on your own instead of taking time in the video. But notice the outcome here. It says do not reject H0. That's our null hypothesis. That's the beginning statement. So it's not that we accept it, but we do not reject it, or we reject it. So those are the two options when we go along. We're either going to not reject it or reject it. We don't ever say the word that we accept the null hypothesis. That's something to think about. Again, just a couple of definitions. We start with the null hypothesis. We assume that that is true. The alternate hypothesis is where the burden of proof is. And there's some other important things to remember. Second from bottom is the most important one for right now. The equal sign is always a part of my null hypothesis. The signs that do not have equals with them, either the not equals or the less than or greater than, are part of the alternate hypothesis. That's important when we start writing these hypotheses. Decisions and errors in hypothesis testing, I will let you read that on your own. It just is some definitions. You don't need to spend time together on it. Our test statistic is going to be determined from the information that we have, and we're going to gather this information and decide if we're going to reject the null hypothesis or not. And the critical value is going to be that dividing point. So it's going to look like our normal curve, just like we have been doing. We're going to find a couple of values and we're comparing them. Am I in the reject area or am I in the not reject area? So many of the things that we've learned in the last couple of weeks will come into play this week as well. Excuse me. So we will have, if it's an equal and not equal situation, we will have a two-tailed test. So we will have the significance level divided into both ends of our normal curve. If we have it to where we're trying to prove the null hypothesis is that we are on one side and our alternate hypothesis is that we're less than, it will be this top situation here. And if our alternate hypothesis is in the greater than, it will be this bottom situation here. So those are different choices we have to know if we're making a one-tail or two-tail decision. Some words, let me move my face out of the way here. I'll cruise over to this other side. There we go. The equality symbols, this is just simply to help us when we have those word problems so that we can know if it really is going to be a greater than or less than kind of situation. Sometimes it's easy to get confused with those. So this chart is helpful. I think it is in your book as well. What do these look like? This page is a little confusing without us working through these together. So let me just point out what parts I think are important. Remember, the equal sign is always part of the null, my original statement. Equals. So we're going to say, well, the mu was equal to 200, 150, 5, whatever it is that we're saying the mu is. And then we're going to have the alternate hypothesis that it's not equal to 200. Those values would be the same. Here we have for the greater than and equal to, there in the middle, we're going to have the equal sign with the null and the not equal sign, the opposite. With the alternative. And here, less than or equal to or greater than. So we will reject if my HO is going to be greater than, right? If it's going to be this one, we'll have to reject my HO. Here we're rejecting if it's less than, if it equals this. And here we're rejecting if it is either greater than or less than, if it's just not equal to it. That will become a little bit more clear, but just how it's written is what I'm interested in. So let's look at a problem. Hopefully this will be helpful. We'll try to work through this one a little bit together and then just show how a change will turn it into a different kind of test and work through that. And that should be enough information for today without us working there together. So we have this, I guess it's a steel manufacturer. They make furniture and they're assembling desks. They have a mean of 200 desks. I think this is per week, standard deviation of 16. And they've tried some new techniques, hired some new people. They want to know if they have done enough to change, notice a change, the weekly production. So remember, our null hypothesis is always going to be status quo. It stays the same. Okay, we're trying to prove that it's otherwise. So this is going to be a case of equals versus not equals, because we don't know if it went up or it went down. The change can be either way. So we're going to have a two-tailed test on this one. We are looking at a sample from last year's weekly production, and the mean for that was 203.5. Information that we need, and the test using 0.01 significance level. So first we have to write, we have those steps that we had in an earlier slide. We're going to actually state the null and the alternate hypothesis. Here it's the null hypothesis is going to be status quo. Mu equals 200. That's what has been going on. We believe that's still going on unless we can prove it differently. And our H1 is going to be that it's not equal to 200. That's it for stating the hypothesis. Okay. We then are going to have our significance level. It's given to us in the problem. And we're going to use the Z distribution since we know sigma, since we know what our standard deviation of the population is. Here is the formula that we're going to be using. Z, we know what Z is, our Z chart. And we know X bar minus mu, we've done that before. And we have sigma divided by the square root of our N. Sample size, we have done that before as well. So how did we put all this together? Let's draw a picture first. It's going to be two-tailed because it's an equal and not equal to situation. We're interested in either if it's over or under, right? We're interested in either of those situations. That would be our alternate. What is in the middle is our null hypothesis. We're not going to reject it as long as we're in that middle area. So how do we get these numbers that are here on this chart? Well, remember that our significance level was 0.01. If we split 0.01 up into two tails, how much do we have in each? Well, we have 0.005 in each tail, which means right here for this whole area, we have 0.99, right? Because that's the area that we're looking at. So if we split that in half, we're talking about 0.495. Looking at that on our chart, we have, for our use, it will be 2.58. I believe the book has a better chart because notice that's just a little bit over. Their chart is going to be just a little bit different. But that's where we get the 2.576. Okay. Ours was 8, right? When we looked at our chart, 2.58. So that is going to be positive and negative areas that if when we do the math, which is over here, if when we do the math, our critical value, our computed value of Z, lies within either of those regions, then we'll reject the null hypothesis and say that our alternate hypothesis is correct. When we end up doing the math, we end up with 1.55. Again, they kind of went out a couple more decimal places, but 1.55 is going to be right in here. Where does it fall? It falls in the do not reject area. Okay, so let's just go over what we just did. We got this point on either side from the significance level. Okay, that's how we did it from the chart, working backwards from that significance level of 0.01. Split it into two tails and find the Z chart number for our critical value. How do we find this number? By doing the math with the numbers that we have. And then we compare the placement of the two. So it does not fall out in the reject, it's in the do not reject. So we can conclude that we have not done enough to change the mean of 200 desks per week, hour, day, whatever it was. We have not done enough to change that, whether in our methods or in hiring new people. So we have not rejected that that is what the mean still is. So let's use that same problem and talk about another way to look at it. Here we're going to say the same issue, but the vice president now wants to know whether there's been an increase. See the difference here? Now we're kind of switching everything to one tail. An increase in the number of units assembled. So we're going to use these same numbers. Let's look and see what that would look like. Our hypothesis is going to change slightly. Instead of it being equals and not equal sign, we will have status quo is less than or equal to. It's always easier to write the alternate hypothesis first. We want to see if it's going to be greater than. So our original is going to be less than or equal to. We have the same significance level, and we're going to use a z-distribution because we still know what sigma is. This time we have the entire 0.01 over in the 1 section, right? My cursor is kind of crazy on this with a double screen. Over in this area, we're going to have the entire 0.01, where on the other problem, when it was two-tailed, we split that up and had it 0.005. Now the whole thing, because we're trying to prove greater than, right? Look up here for your little symbols of the hypothesis. When I look up, this area is 0.5, and I minus my 0.01, so I'm looking up 0.49. I get a critical value very close to 2.326. Sometimes their chart is a little bit more specific than our chart. So that gives me the critical value. Now I have to do the math and compare where my value is. So when we do the math, we still get that same 1.55. And where does 1.55 land here? It's going to land in the do not reject again, right? See if it says that. Yes. 1.55 does not land in the reject. It is still in the do not reject because 1.55 is between 0 and 2.326, right? It's going to be right in here. So we're concluding that the number of desks assembled, that mean number of desks in the last 50 weeks is not more than 200. So we didn't move the needle any on that. I don't know that I want to go into this next part or not, so maybe we'll hold off on this. If we have another snow day Wednesday, I think I'll pick it up from this point. But here we're going to be talking about when the population standard deviation is unknown. Guess what we're going to use, right? Instead of the z-score, we're going to then switch to the t-score for that statistic. But I think this gives us enough information, and I'll write up a little bit of an assignment for this. Hope you have a great snow day.